everyone, welcome to All Things Indian Friendly Voices. Uh, I don't know, it's a kind of a strange coincidence. Myself and Suresh, we don't plan anything for to coincide with a specific day. Some of you pointed out is some kind of Purandaradasa's birthday when we recorded, something like that, so when your music episodes. But today, ironically, today is a science day. And today we are going to talk about physics. I don't know, recent developments, more contemporary period, and even those who pursue science and curriculum in the college or university, beyond the point when they get a job, we all forget what physics is and we never keep up with the latest developments, maybe on Twitter, social media. One of the usefulness of is that we hear some terms like LIGO. So I don't know what is that. So everybody was talking, they getting excited about it. So some kind of a God particle. So somebody found it and everybody said Eureka. So I don't know what that is, to be honest. And so we have a very wonderful friend who is very knowledgeable, who is going to explain to us in a very simple terms what these are.
Yeah,
So yeah, thanks, Suresh.
yeah. Thank you, Rajman. And let me introduce Nanda to you. Nanda has, I know him and he's been on Twitter. I think I forget his handle is. Anyway, I'll give you his handle. I think it's Ion Shaker, right?
Ion
Ion
handshake.
handshake.
Yeah,
Ion Shaker,
exactly.
Ion. I mean, he is like, so you can understand he's somewhere in particle physics because he's shaking the ion. So actually, Nanda, whose full name is Nandhakishore Perarulalan, he's currently pursuing his PhD in what is called as the cold atoms group. And this is in the School of Physics and Astronomy in the University of Nottingham, which is in United Kingdom, the Britain. Now, he received his bachelor's from Chennai. He was a bachelor's in engineering from the Anna University. And then for his master's, he went to USA, where he completed his master's from the University of Cincinnati. Now, he's also worked for a year as a research associate at Tampere University of Technology, which is in Finland. And his area of interest include experimental AMO. AMO full form is atomic, molecular, and orbital physics, quantum sensing, and computational electromagnetics. So this is the overall picture about Nanda. So let us start discussing the latest trends in physics with him. So for this, I will request Rajmohan to start the proceeding,
Yeah.
and up to you, Rajmohan.
Yeah, thanks, Suresh. Nanda, before we start asking serious questions, it's just kind of a very curious. I mean, like you can tell me. Most of us will watch Hollywood movies and series and especially American series and Netflix or something. Does really nature abhor vacuum? Uh, like uh,
About
Aristotle is supposed to have said, nature abhors, hates vacuum. But I also read somewhere that 90% of what we see is non-matter or whatever. We don't know anything about it. So
yeah, so that's kind of like the dark matter research that's going on currently. So is matter really all that there is in the universe, or is there something else that we don't really see? So that part of research comes from astrophysics. I mean, Dr. Vera Rubin started this. Vera Rubin was the person who started dark matter. So the idea of dark matter itself, it begins. Okay, so let me put it this way: we know that there exists a solar system, and the sun is in the middle of it. Mercury revolves around it, and Neptune revolves. It's the last planet. The revolution or the speed with which the Mercury revolves around sun is far more quicker than that of Neptune. Mercury is closer to the sun, and it completes one revolution in a time that's or in a span that's shorter than that of Neptune. And you know the order. It goes from Mercury, Venus, Earth, and goes all the way till Neptune. This is something that you expect normally through Newtonian physics or Newtonian dynamics or Newtonian mechanics. For example, so when Dr. Vera Rubin started her research, she was really interested in galaxies. She wanted to observe the spinning and the rotation of galaxies. what happened was she started using telescopes, essentially getting time on telescopes from various research observatories. Mauna Kea, there are plenty of observatories around USA and around the world, from which she started observing the Andromeda galaxy. There is the M31 galaxy, and there are many particular specific spinning galaxies, and started observing the way they spin around. So this is where things start getting interesting. In a conventional normal system, you'd expect the planet that's closer to the sun, or the body that's closer to the one that's revolving around, to be far more quicker. In this case, the centers were far slower than the edges. So if you've seen the Andromeda galaxy, it's in a spiral shape, just like how Milky Way is. As it starts spinning around, the edges revolve at a speed that's far greater than those in the center. The center. When that happens, this is an anomaly, something that had not been predicted before through Newtonian physics or Newtonian dynamics. And it is at this point that Vera Rubin starts, hypothesizing about dark matter and what kind of, other possible matter available within the universe. So this speed anomaly can actually be explained by the presence of a greater field of gravity, and that gravity quite directly corresponds to matter. Vera Rubin said this matter is not something that's been detected never before, and called it dark matter. So that's the way the entire dark matter theory starts being built up. And does nature abhor vacuum? We don't know, because we haven't really gotten in there.
Yeah, I read somewhere that this is also to account for the weight of the universe, something predicted by Big Bang, but the actual weight that is calculated based on thing didn't match, and therefore it is also something which goes into dark matter type of thing. Is that understanding correct, or?
Yeah. So in the case of astrophysics, most theories start in a sense. People start observing things. They expect systems to behave in a certain manner, and somehow there is an anomaly. Somehow there is an anomaly. So that's how the entire field of quantum physics starts. There is black body radiation. You expect black bodies to emit energies continuously, but then there comes a point when Max Planck comes and says it needs to be discretized. That's how this happens too. Here, Vera Rubin starts observing the spinning galaxies. The speed does not add up, and that's when dark matter starts coming in. So once you have a certain understanding that that is a part of the universe, matter that cannot be detected, this can now be used to build on and see how exactly this corresponds to the weight predicted during the Big Bang, and how exactly the weight of the universe is to be. So I would say it's an ongoing process where we are still into researching a lot of things about dark matter. We're trying to experimentally detect them.
So. Okay. The question is, just one last question before I let it, is that this seems to be very similar to how ether was sort of hypothesis, right?
Yes, exactly.
Because ether was supposed to be similar to dark matter. You can't trace it, you can't do it. But it turned out to be a different issue, like the special theory of relativity and others. So it's a possibility
they were hypothesizing with luminiferous ether for a long time, and then Michelson and Morley came in and did their experiment.
That did the experiment, and
that detects, yeah.
No, what I meant is, it could also be that someday some experiment would prove that either dark matter exists or doesn't, and you may come up with something totally different for all that.
Yes.
But the state of affairs is that it's not yet proven, right?
Yes. So the hypothesis now seems to tilt slightly in favor of dark matter, but as always with science, we don't know. Something else might come up and disprove that there is no dark matter, or we don't have WIMPs or SIMPs. They're called weakly interacting massive particles. That's part of the particle theory, and that's what all dark matter experimental detectors are trying to find out at this point.
Oh, okay. So we do not know. That's what you said, whether nature. I mean, obviously Aristotle wanted certainty and everything, and like Robert De Niro, he said, "Bloody Greeks." Okay, so they don't know. Yeah. So basically, that we will start with a question on supercomputing. Well, in fact, during Minsky's time, they even came to the conclusion that there was a lot of research articles, even books were written, that in fact whole human life is a kind of computing. Everyday life, everyday process is nothing but computing only. So what is this supercomputer? Supercomputing is like superstar, like Rajinikanth of computing.
No, I think Rajmohan, you probably meant quantum computing.
Sorry, sir,
Uh,
quantum computing. Yeah,
yeah. So essentially, yeah, because the whole of the world is nowadays talking about quantum computing because Google has probably
yeah.
jumped into it, right? So yeah, Siananda.
So before we get into quantum computing, I thought it will be better to give you a quick background on quantum physics, or how exactly we get to quantum computing, or where we
Sure,
are today.
sure.
So the thing is, at one point, Newton comes up with his laws, and sometimes in the 1600, I believe 1603, 1604, or sometime later than that, 1600 something. So Newton has completely come up with his laws that explain the workings of the day-to-day matter, and how exactly dynamics happens, and and all those things. That was later developed by you come up with Laplacians, you come up with Hamiltonians to explain the mechanics of day-to-day objects. At one point, Thomas Young starts doing his famous double slit experiment. So the idea of the double slit experiment is you have a particular source of light, and you have a grating. A grating is just like a mirror that lets a lot of things to pass through one small slit. And you, in the case of the double slit experiment, as the name makes it very clear, you have two slits, one source of light, and that source of light is going to pass through the two slits. Normally, what you would expect with Newtonian physics, so you have let's say a cardboard where there is a single slit. You take a torchlight and you just switch on light. Light passes through just through the single slit, and you get an impression in the screen behind, or in the object that you're trying to detect behind. With respect to one slit, you just see one wave.
Correct.
Now, what Young did was he took this particular source of light, had two slits, and passed it through. You would expect just two slits to happen, but no, that's not what happens. You get a pattern of light and dark, of, let's say, fringes. You have a consistent dark, a very strong bright light in the center, and then there is a darkness pattern, and then there goes on into another light and dark completely mixes up together. And this kind of sets into place the entire quantum mechanics revolution. This experiment was done sometime in the 1800s. After that, the entire quantum theory starts catching up. Max Planck says that energy only needs to be emitted. And what exactly this experiment proves is that there exists a superposition of the two light waves that pass into the two slits. And that's what, once you start observing, unless until you start observing, they remain in a state of superposition. Now, cutting from there to what we are talking about right now, it is this particular property of superposition that we're seeking to exploit when it comes to quantum computing.
Mhm.
So in terms of conventional computing, what you do is you have two bits. If you want to add 1 and 0, you have two bits. You use a half-adder circuit. So with respect to, as you keep adding the number of bits, what you can do is only serial processing. You can only start having individual, let's say, let's say there are 4 bits. You can go from 0000 to 1111, and each and every one of these states will have to be traversed through serially. So when it comes to, when you have this particular property of superposition, and you have, say, 4 qubits, you can ideally have a lot of things coexist or exist in all those 16 states. It's kind of, that's how it's explained. It's bizarre. It can confound people who are watching this, but despite that's how nature behaves. And we are trying to see if we can essentially tap into those properties and see if we can build machines based on that. That is going to help us compute.
Yeah. So let me ask you this question. See, superposition, which you mentioned, right? So I think if I remember my physics of a long time back, is that if you were to take it as just waves, this two slit experiment makes sense because of the diffraction pattern formed because of the interfering of two waves. I think it starts making no sense when you start observing each slit and then the pattern turns out to be a standard pattern, the Gaussian type of a distribution, right?
Yep.
So I think the superposition which you are talking about is that a state exists in multiple positions, the Schrodinger cat type of thing, until you measure.
Yep.
Correct. So
Yep.
the question now is, as you said, if there are 4 bits and each one is in a superposition of, say, 2, I mean 4 into 4, whatever you call 16
Yep.
states.
Yep.
So what we are trying to say is, are you going to get a single state out of that when you measure, or if you can? But the problem of quantum mechanics seems to be the randomness, because you cannot predict what state it will come out to.
Exactly.
So what is happening here?
So when it comes to building quantum computing machines that can be put to use, one of the biggest problems that we face is noise. So the moment you start building these qubits physically, qubits are just mathematical systems, and there are many ways you can go about building them. There are superconducting qubits, there are trapped ions, and many systems that you can try and actually physically realize these things. And one of the foremost problems that you face is noise. And that's why most quantum computing devices are situated in near absolute zero temperatures. You will see those chandelier-like devices. If you just go up to Google and type quantum computers, you'll see a chandelier-like device. So that's like the dilution fridge that's trying to cool down the quantum chip to a near absolute zero. That's minus 273 degree Celsius.
Celsius.
At that point, the point of doing this, the point of cooling it down, is ensure that noise or external noise does not affect quantum chips or quantum processes. So in order to get back to your question, so how exactly are we going to try and measure this? What we do is we run the experiment repeatedly. We run the code that we are trying to solve, or the optimization program that we are trying to solve repeatedly. We take 200 shards. They're called shards within when you're writing quantum code. So you can essentially program one quantum computer. IBM has put out all their quantum computers on the cloud. So what you can do is use Python and start coding up, and you could connect on the cloud to IBM devices. And what we do when we are trying to do this is run the experiment repeatedly to see to get a lockdown upon the exact state that we are trying to narrow down upon. And that is trying to eliminate the measurement error and the noise error as much as possible. And the
for the benefit of our viewers, I mean, what exactly are the practical benefits for ordinary people of this quantum computing?
That's a good question. So, for example, the applications are immense, basically. So, but the era that we are right now, so the point that we are right now in terms of history is basically, it is very similar to how computing began when Charles Babbage and all those people were trying to develop conventional computing machines that we're using right now to talk to each other. So this is the kind of development cycle that the entire physics is going through. Right now, we are in a state called noisy intermediate scale quantum. So the devices that we're using have a lot of noise. But when it comes to optimization problems or very specific type of problems, these particular devices perform really well compared to conventional computing systems. So let's talk about batteries. Batteries is one place where quantum computing is supposed to create revolutionary progress. So battery materials that we're using right now, most of them are lithium batteries. They're able to store energy to a certain point of time. You keep charging batteries as and when you come by. So the point of using quantum computing within battery research is to try and see if we can simulate new materials, tap those properties, and see if we can generate and come up with better batteries that would be able to hold new materials that would be able to hold energy for a far longer time. Let's say, the old Nokia batteries used to do that, but something far more progressive than that. So
okay, I just wanted, sorry for the interruption. I just wanted something. For example, if I'm running a program, current computers, we know how they would behave, right? If you are into the hardware, you will know how the NOR gates or something, right? The whole XOR gates is what NOR gates or whatever gates that they use to build the whole system nowadays, right? The only one type of gates, I think, which get there. So we know exactly how things is go, where the zeros are going, where the ones are going, where they're adding up, what logic is circuit is there. So similar to this, what will be that in a quantum computer? Because this is like you have a logic diagram, you have the OR and NAND gates, I think, whatever, The NAND gates are there and you can write your logic clearly and they'll go. But when you're talking about superposition of state and such, would it still be something like this? Or as you said, would it be 10 different gates, 10 different architectures are running at the same time, and out of the computational speed that you get, you choose one of them, or what is it that
No,
happens
so
internet?
essentially, we were talking about NAND gates and the conventional classical logic. So
Correct.
compared to that, quantum mechanics, quantum computing, since it runs on the backdrop of quantum mechanics,
Hmm.
has something called the block sphere. We are using, so a conventional bit can exist between a 1 or a 0. You have a charge, you have a voltage, or you don't have a voltage. That's the
Correct.
way you continuously calculate it.
Correct.
In this case of superposition, what happens is the state is described by something called a block sphere. So each and every coordinate within the block sphere is something that gives the state of what the system or the circuit is trying to compute at that point in time. So
Mhm.
so you're pushing it all through various gates. So you have, just like you have NOT gates, you have C NOT gates here, control NOT gates. So
Hmm.
two qubits can be combined together using this particular gate. And quantum computing, there is something called the no cloning theorem, where you cannot copy the state from one to another. So we have to make modifications according to that. So
Mhm.
when all of these are combined together, you put them, you formulate a circuit, and then you finally measure them. You arrive at the exact state that you require. So you don't have to keep changing the architecture of the circuit each and every point of time.
Ah.
But for a given program, you have a given circuit. So that's how it works.
Oh,
And
you are
but with
okay.
respect to optimizing the system itself, but with respect to coming up with various kinds of architectures where you try and talk to QRAMs, they QRAMs are the quantum mechanical equivalent of classical RAMs. We still don't
Ah.
have them in
Oh,
production or even conceptually.
okay.
But when
Okay.
you're trying to use memory and you're trying to integrate it with all of these
General
computing
purpose.
hardwares, then
Okay.
the architecture is going to obviously be different.
So what you're trying to say is that currently it is not like a general purpose computing, but a specialized thing that you build a circuit for a
You-
particular problem.
yeah,
And
exactly.
within the parameters of the
Yes,
problem, it will solve the problem. But
problem.
the same computer you cannot use to solve a different problem.
Not exactly. You
Not the
can use
same.
the same hardware, but you have to, try and
Reprogram it.
reprogram
You have to reprogram it. Okay. Whatever you
reprogram
call
it.
as
But
if.
yeah, that can be developed in due course, and that's where it is at. It's
Oh,
used for
okay.
extremely specialized purposes, but these
Okay.
purposes are like cannot be solved,
With the normal
using
computer.
classical computing.
Okay.
And that's what Google proved in 2019. So
Okay.
when they're talking about quantum supremacy,
Hmm.
they said this is a particular problem that cannot be done classically, but we have solved it using, or we have simulated it using quantum computers.
Okay, like whatever they call the NP hard problem type of thing, or
Yeah, combinatorial optimizations.
okay,
That's NP hard basically. So
okay. So that's NP hard as far as the conventional systems are concerned, but
so,
on a
uh,
quantum computer, it is solvable.
solvable. Yeah.
Yeah, this leads me naturally to the next question, which I was wanting to ask you. So what seems to happen now is that one of the NP hard problem, not really NP hard, but one of the known ways of doing cryptography is that everybody knows the algorithm, you don't know the key,
Yeah.
right? And the whole idea of that is, if you um, want to do a brute force attack on this, we know the algorithms and we know the size of the key because it's defined standard. So let's say it's a 256-bit key,
Yeah.
and then you put up the combination of 2 to the power 256, you should somewhere strike it. But the idea is 2 to the power 256 combinations to run even on the best
It's going to take
supercomputers
an
would
immense
take
amount of time.
immense amount of time. Sometimes it, but like you want to break somebody's password on or the OTP type of a thing within some time. So if you take it for 1 year, 2 years, it is not going to
Yep.
be there. Therefore, that's how you safeguard. But now, as you said, if quantum computers are going to be able to compute these at a reasonable amount of time, so how does this impact the whole security of the internet as a whole? Because this has greater implications, right? So the keys can be broken anytime, and your RSA keys and others can easily be broken when it comes to this.
So now that you mentioned RSA, and so the entirety of a lot of public key cryptography systems, including RSA, depends upon prime factorization.
Correct.
This year, it's often hard to grasp. You have one particular number and it can be factorized into two different primes.
Primes, yeah, large
2021
primes.
is basically 43 into 47, and it doesn't strike someone that quickly.
That, yeah.
So the moment we come in and start using quantum computing, it starts using Shor's algorithm. Shor's algorithm is the one that's used for prime factorization in quantum computing, and it can get there in terms of reasonable amount of time. And in terms of security, this does have larger implications. But one, we still aren't there yet. We cannot, try and run it to 2 per 256 level. We still don't have the hardware to get there, but it is going to get there eventually.
Correct.
That's point one. And then people have also started thinking about post-quantum cryptography. So once, if these systems start coming in, how exactly are we going to create our own cryptography systems in order to catch up with them? And that is where I'd like to bring in another quantum property, entanglement. Entanglement is this particular property of quantum systems where you entangle two very specific, let's say, bits or qubits in this case.
Correct.
Even at a far longer distance, one would be able to replicate the property of the another. And the moment you start measuring, it's going to affect the quantum state or the wave function of that particular bit, in turn correspondingly affecting the other bit present in the Alice. So let's say Alice and Bob are trying to exchange messages. Alice has one particular qubit stored within him. He has he has sent an entangled bit, and he has sent it to Bob. And there is an eavesdropper, Eve, who's essentially trying to crack the communication between Alice and Bob. Eve is trying to measure the state of the system. That the very act of measurement is now going to change its state, as we had mentioned earlier, as we were talking about earlier. And that will let the person know that they have that is an external attacker who's tried to read it, because the state has changed within the two entangled qubits. And that's one idea that people are working on, trying to come up with in terms of algorithms to try and see how this can happen.
I see. Okay. So yeah, so we are talking about this entangled state. I think this is the one which got into that Einstein's paradox and
EPR paradox.
And then Bell proved that inequality.
Yes.
Okay. So
talking of entanglement and all from ordinary point of view, okay, one more term. What is quantum sensing? Is it some kind of sensing, like I don't know. If you give a wrong answer, okay, it's okay, wrong answer, wrong analogy. That is like the movie Robo, where Chetty just in one flow it sees everything. Something like that, some kind of a super sensing.
So let's say quantum sensing is a particular area of interest of mine, because that's what I'm working on right now. Let's talk about quantum sensing in terms of its measuring of extremely tiny quantities, extremely low. Something that cannot be measured conventionally. So let's say there are multiple physical properties that continue to govern the way. So we are setting the room temperature, there is the mass, there is the length, and you can only go up to a certain extent in terms of it, which is almost always in terms of nanoscales. Let's say 10 power minus 9 meter, 10 power minus 9, Tesla or something like that. So when we are starting to use quantum properties, when you're trying to use quantum sensing or quantum systems to do this sensing, we would be able to measure and detect quantities that are way lower than what we do currently. And that is going to have an immense amount of applications in terms of a lot of fields. For example, healthcare is one. So right now, what we're trying to think about, we are communicating based on, we are thinking, and that's neurons. Neurons fire up and they use magnetic fields. Those magnetic fields are extremely low, in the order of femtoteslas, which are 10 power minus 15 Teslas, 10 power minus 14 Teslas. So if we're able to use quantum sensing devices, we'd be able to essentially try and measure the magnetic fields, biomagnetism being generated within the human bodies, animal bodies. We can use that in terms of healthcare, in terms of trying to detect Alzheimer's or your early patient onset cancers and all those things. That would help you in terms of diagnosis and other things like that. Again, this has a lot of applications in terms of security. Security is what I'm working on right now. So you have an airport scanner. You are essentially, so what most modern day scanning devices do, let's say metal detectors into which you're walking. Metal is detected based upon the magnetic field that it emits. You're looking at the eddy currents being generated and magnetometers, and you're using magnetometers to detect the magnetic field that the metal actually generates. So right now, copper or aluminum or those kind of materials is the ones that are being detected quite easily. Let's go up to a low scale. Let's say there are plastic explosives that are being transmitted within let's say it's security purposes. If we are able to sense the magnetic field that that particular material is able to emit in order to get to the conductivity of that particular material, you can use quantum sensors that would be able to pick up on those magnetic fields being emitted, and that can actually help us see if something is being basically crossed over. Once you start scanning it, you can actually get there. And security is another possible application. The entire area of quantum sensing revolves around getting to those measuring those undetectable quantities.
Now, if I just have one follow-up question here before I ask the other question is, now at these low levels, when we are talking about, typically the act of observation itself seems to affect the observer, right? That's the
Yep.
whole idea of quantum. So if
Yep.
you are going to measure a 10 power minus 14 Tesla type of energy, right, you have to probably look at how you measure, you are interacting with that level. So does this distort the field when you measure? I'm sure that's one of your research issues.
Yeah. I mean, that's actually an interesting question. So how exactly you design your control system, what interacts with the field itself, that is an extremely important question. So right now what people are doing is they use this thing called optically pumped magnetometers. There is a particular laser device that is being used to, that is the probe field. Probe field is the laser that is directly interacting with the material that you're seeking to sense, and then there is the control field. The way you design your control fields, that is going to impact the way probe is going to interact with the material that you're detecting. So you can essentially modify your control field, use algorithms to essentially control it, active control, see how exactly it's interacting with your material that you're
Okay.
supposed to detect.
Okay.
And then based upon that, you can essentially see at what point the paradox comes into play, or how exactly the measurement. And also these effects are way much more prominent in when you're going to start going very
Correct.
lower. At this effect, it hasn't affected us to that point. That's
Okay. No, because I was asking you because, as you said, if it is used on patients to do this sort of scanning to find out Alzheimer's or that, because if you impact the magnetic field of the brain, that would have a real impact on the patient, right?
No. So that's the point. So conventional MRI systems, the ones that we're using right now, so there is a particular property called magnetic or nuclear magnetic resonance, NMR. So that is what MRI scans essentially try to measure upon. So when you're trying to place your conventional MRI device, so when you're getting into MRI, people who have taken scans will know that they'll remove all metallic objects from you. People who use pacemakers aren't allowed in there, and those kind of problems. So if at all is so when we get to this point where we start using quantum sensing to measure these fields, we'll basically have an idea of, you don't really have to go into a machine. That'll be just like a helmet that you can wear and start measuring the magnetic fields that are being present within the patient's head, and that in turn can add up to biosafety.
Okay, I understand. What I just meant was, at those levels of measurement, does that affect the
no, that there is
magnetic?
no external interaction. What we're trying to do here is simply measure. We are interacting.
No, I understand. This is because you're measuring the wave, right?
Yep.
So it's the one which comes out of the head, or you send something inside.
So what we're sensing is the spin. So there is nuclear magnetic resonance basically measures. There is this particular property of atoms or electrons called the spin, and that spin creates magnetic fields in turn, and that's kind of polarized when you're essentially using an external magnetic field. And the magnetic field measured due to the spin is what you're measuring. So that is.
So basically, you detect using the external magnetic field. You just detect. Okay.
Yeah. Okay. Now, so you spoke about one sort of application that is there. What do you see as some changes due to quantum computing and others? Like things like GPS and things like what do you call security apps and others. Security we spoke a bit about,
Yeah.
right? But things like GPS and all, because they measure at a very large distance, are there going to be any impact on such things?
So, GPS, the way GPS is done is like you have a particular device, a mobile device, and that communicates to a satellite.
Satellite,
What
yeah.
you're trying to do is you are trying to triangulate the position of where the device is present. Essentially, that satellite in turn communicates with another base station from where that's basically your reference point or your location point. What you're trying to do is triangulate that the exact location of the device. So for which the device itself needs to communicate with an external source.
Correct.
So when it comes to quantum sensing, as I was talking about magnetic fields and measuring low magnetic fields, we can think about one ancient device that was used to navigate around, the mariner's compass. Basically, the mariner's compass was something that was used to navigate, find out the directions whenever sailors were sailing within seas and things like that.
Correct.
And that worked on the principle of Earth's magnetic field. So what we're trying to do with quantum sensing is, in a sense, trying to replicate what the mariners were once doing.
Oh.
So try and see how exactly the Earth's magnetic field is going to affect the position or the location that you're standing on. Measure the Earth's magnetic field to see what is the direction in which you need to proceed.
Mhm.
The advantage or the advantage is that you don't really need to talk to an external device. Your mobile phone or any GPS measuring device, at one point of time, it positions itself globally. That's global positioning system. So you don't really have to talk to a base station or an external device to try and find out your position. And that's what that would be the most direct application of quantum sensing upon GPS or in terms of any other security devices.
No,
So you have radars. Essentially, you're sending out. You have a particular magnetometer. You're sending out a radar, a wave, and you're trying to use radio detection and ranging to get those waves back. So you'd be able to detect their location to a way greater accuracy with sensors. And that's,
so let me just again try to understand this. So currently also we have magnetometers, right? In some of them, so not all phones probably have, but some of them have. So you can run a compass from there.
Yeah.
So what is it that quantum computing does, which cannot be done with normal computing if you have a magnetometer? So what's that difference?
So the normal magnetometers, let's say the phone magnetometers are the ones that we have. Our Earth's magnetic field is 0.5 Gauss, which is approximately 5 to 10 power minus 4 Tesla. So that's the range at which we're actually reading right now. So with respect to quantum sensing, when we're starting to use these particular quantum sensors, we can go up to an extremely low level, as I was talking about it earlier. This is the strength of the Earth's magnetic field itself varies along the surface of the Earth.
Correct.
So this is what I gave you. The number that I gave you is the average point of it. So we would be able to get to a better level of specificity, a better level of sensitivity using quantum sensors. That in turn can be used to locate at what point on the surface of Earth you are.
Okay, so essentially you are saying the way this whole thing works seems to be that as you proceed across any point in time, the magnetic field actually varies. Right? Varies, yeah. So the magnetic field varies, and I think the G value also varies, right?
Yeah,
I think
G varies.
G varies. So I mean, for all the missiles and all, they need that. So the magnetic field varies. Currently, we are able to detect it only to a certain extent. Therefore, you are saying that, okay, this guy is within this 1 kilometer range or something. But if you detect it much lower, so essentially it also means that using the sensors, first you should have a map at that level, correct?
Yeah, that will help you to try and narrow down upon where you are.
No, what I meant is you should already have a map of how the Earth's magnetic field varies.
Yes, definitely, yes.
But that itself would be a lot of data to be there. Right?
Yeah. So essentially, one particular area that we're looking at is also inverse problems. We're trying to see how exactly the magnetic field within Earth varies, and this can also be used in geosurveying, mapping, and essentially trying to mining.
But this is not based on any fundamental thing, right? This variation is just you have to measure and get it.
But this is applied physics. No, this is not pure physics. This is rather applied.
Yeah, it is rather. I mean, what I meant is there's no particular formula which will tell you put the coordinates and get the
Yeah,
exact
but
value.
we can
So you
eventually get
actually,
there is what we're hoping for. So
oh, that means they are thinking that there could be a formula,
yeah, that
or
we
if
could
not,
get there.
if not fundamental thing formula, but some at least heuristic is could
Yes,
come in.
yes.
Okay,
So
okay.
we have this whole field called inverse problems, where uh, you don't know what the system is. You only have the output using which you can get back to the system.
Oh,
So
okay.
that's
It's
something
like
that's really,
something
really,
like big data type of
yeah. You could say that.
something like that.
Mm.
Okay. Yeah, Rajmohan.
Yeah. So, I mean, that level of accuracy is really scary. I mean, this kind of a technology goes into wrong hands, Dr. Evil. I mean, no, you not be Dr. Evil, anyone else. Uh,
so so
but
that's why
also,
there are a lot of trade restrictions and security based restrictions, and you need to get through security clearances to actually start availing this technology, which is a
oh, okay. So, but I mean, the way I'm telling is, and also that people have put a filthy number of satellites which are dead, unused, and non-functional. I don't know that because why I'm saying this next question is relates to the clean and safe earth. So, but well, I don't know. There's always a saying that how often do you look at what the man is wearing, and it's also true that how often we look up. Even if you look, when you have some kind of a tool by which we can see the dead satellites just hovering over our earth. Basically, what I said was next question. The next question is about the kind of what we are always, I mean, to thinking back, maybe when Suresh just fed me all these things, I was just thinking through maybe 100 years or so, or 200 years, we have always been looking for alternate forms of energy, which has always been met with resistance, or sometimes which are dangerous consequences. People who are looking for something different. And what we have is fission. And what about what you mean? What you can tell about nuclear fusion? And if I remember correctly, some 10, 15 years ago, we had something in Paris, in France. I mean,
So
will it eventually give a, I mean, safe energy, nuclear energy safe?
I mean, it's again one of those concepts that have been that is physically feasible. We have the laws that can help us get there. The challenge is in engineering. We do not know if it will scale correspondingly or if it will give us the exact cost benefit. So the idea of fusion reactors and using fusion reactors to generate clean energy has been around for a long time. I think even since the 60s or 70s, people have been talking about it. And this particular attempt that you're talking about since 2005, this was ITER, and it was pioneered by the European Union. This is the International Thermonuclear Experimental Reactor. And it's been done in phases, and people have been working on it for close to 2 decades now. So the idea of nuclear fusion, as you mentioned right now, is that it is quite capable of giving us clean energy, give us energy where there is no radioactive waste, where you don't really have a lot of greenhouse gas emission. But the problem is we don't know how commercially viable it is, or whether we can use it's a 10 billions and billions of euros and dollars that you need to pour into this project, and we don't know if it eventually get there. So that's the kind of the challenge that we're facing in terms of fusion reactors. The idea of fusion reactors is basically what you're trying to do is to replicate the same energy mechanism that stars use
Yeah.
for their energy generation itself. The sun is a perennial source of energy where there is always energy that's being generated apart from the life cycle of the star. So what happens in sun is that there is particular fusion reaction that keeps happening between hydrogen forms deuterium in turn forms tritium. And is there some way that we could tap into this fundamental property of stellar energy and we could recreate that here? And that's what ITER, or for that matter any other fusion reactor, tries to do. So the advantage is that you don't really have any radioactive waste. You don't have any greenhouse gas emission, no carbon dioxide, no methane, or anything else. This particular entire clean idea is achieved because we have it's just hydrogen atoms, and the best that you'll get out of it is tritium occasionally. But even then, that's going to be unstable, and that will not cause any kind of large scale industrial disasters that you've seen on the likes of Chernobyl or Fukushima or something like that. So this particular idea, fusion reactor, is made possible because of plasma physics. Plasma is this particular, people say it's the fourth state of matter, or there are some people who argue it isn't. So, but plasma is essentially extremely charged nuclei. So what we're trying to do within a fusion reactor is take up hydrogen, put it in there, supercharge it, essentially try and strip all electrons out of it, just ensure that it's just nuclei, and then you're trying to combine those two, fuse those two. And this particular plasma fusion can be achieved using large scale magnetic fields or large scale lasers. These huge magnetic fields require superconductors in turn, and that is where controlling these magnetic fields is where I've done the slightest amount of work on. So when we try and fuse these two together, we get an immense amount of clean energy, and we are trying to tap, which is dissipated in the form of heat, and we are trying to trap that through steam and start generating it. So whether we would be able to get there is the greatest challenge.
Okay. So theoretically, it has been shown it is possible on a lab scale, let us say, but you're probably looking at a large scale production. Then we don't know what other issues.
So the ITER itself is costing quite a lot of money, and this has been going on for close to 20 years. And then people are talking about how exactly this money itself could have been spent on other forms
of energy, maybe solar or something like that.
So we could start looking at material research in terms of tapping solar energy or something like that. So that's one of the challenges that fusion energy will have to overcome, and we don't know if it is going to be there yet. That's where it is at currently.
It is at this point. Now, so coming to these sort of strange ideas, not strange ideas, these sort of breaking ideas and all that. One person who seems to be always in news, at least on Twitter world, is Elon Musk, right? So Musk is as that. I think the SpaceX and all that something, right? Yeah. And then of course he's been talking about this Hyperloop a lot, right? So it's about how fast things can go, etc., and all that, right? So can you give us something about Hyperloop? Is it possible? What is it, and what sort of benefits it's supposed to bring in, and what are the actual physics involved in realizing this?
So essentially, Hyperloop was this idea that Musk came up with in 2013. He published a white paper or a draft that essentially details his argument as to why this will be a viable or a viable commercial form of transportation. He called it the fourth mode of transportation, or rather the fifth mode of transportation. You have land, you have air, you have sea, and within the fourth mode, he called it Hyperloop. So the idea is that you have vacuum tubes all along. You generate and put vacuum tubes from one place to another, from one point to another. And then you move within those vacuum tubes, use pods to move within those vacuum tubes. The point of using vacuum tubes is that there is no friction. You eliminate the idea of friction completely. There is no aerial friction that you have to face when you're traveling on planes. There is no physical friction that you have to face when you're on cars or land-based transport. So because of this, you'd be able to reach transonic or even supersonic velocities quite easily, and that's the biggest advantage of doing this. The challenges are immense again, in terms of both the physics and how exactly you're going to try and build this, and in terms of the ecological and the engineering effort itself. The first things first, you go from one place to another. Can you do such a large tube where you're able to maintain perfect vacuum? There is always going to be so atmospheric pressure is approximately 10 per 5 pascals. The rooms that we are sitting on approximately have 10 per 5 pascals around them. So maintaining vacuum is 0 pascals, ideally 0 pascals. So within these in this particular long stretches, would you be able to maintain vacuum? That is one huge challenge. And the next part is how you design the pod, and how exactly is the pod going to move ahead within these. Let's say there is a syringe, and you're essentially sucking the piston of the syringe. You've sucked air completely in. Now close the bottom of the syringe and try to push it back in. You can't do it. It's going to be really, really hard, because there is air cannot escape out of it. Air is going to simply push it back in, block it. So that's the kind of the engineering challenge that you're going to face when you're trying to move within the Hyperloop. There is a particular idea called Kantrowitz limit. Even though it's supposed to be perfect vacuum where you've pumped out all air from it, it's not going to be ideal vacuum. There is no way you're going to be able to maintain 0 pascals over long stretches, say 200 kilometers, 300 kilometers. And the moment air starts seeping in, you will face this problem as you're trying to push ahead. So there is this entire idea called the Kantrowitz limit. He was a fluid and mix engineer from America, and he presented this idea, and Musk kind of started talking about it within the context of his Hyperloop. So the challenge, or various teams around the world have come up with various concepts, various ideas to try and eliminate this problem that you're facing when you're trying to push in through the vacuum tube. And you could use pistons, or you could use propeller fans. Some teams try and elevate them using magnetic fields and all those. But still, it remains a key engineering challenge within Hyperloop. So at the moment, I think Virgin is really interested in building this technology. Virgin by Richard Branson. So they do a lot of freight transport. So they at the moment it is far more applicable towards freight transport than towards human transportation, because there is a lot of risk in there, and in order to mitigate that, freight is comparatively safer. So you can just put it in there, and that's why Virgin is betting big on this. And I think they did a demo. They've been trying to do scale demonstrations. First, we'll scale for say 1 kilometer, then for 10 kilometers, then for 20 kilometers. And I think they came up with a demonstration last year. So I think it has a future in terms of freight demonstration. But in terms of human transportation itself, it will have to wait quite a lot of time. And it also is viable to build such long tubes.
Yeah. So that was my follow-up question, actually, in the sense. See, there are two things here. One is you have to build the tubes, right? And the material, and others one. Second is you have to maintain the vacuum, as you said, as one of the big things. And if because you're traveling at high speed, even a small friction can cause lot more loss of energy. But assuming that we are traveling with a lot lesser energy spent in this, but would it compensate for the amount of energy you will have to put in to maintain the vacuum inside?
Yeah, that's again another key challenge in terms of ecology. We'll have to look at the cost benefit and see if it is a viable solution. Maybe it can work for small scales. Let's say in a crowded city,
you transfer.
Yeah, you can do this relatively easily. So for around 50 kilometers or so, you could do this relatively easily. But you're going to do this for say 500 kilometers, then perhaps not that feasible.
Yeah.
So this still work within small scales.
Yeah. So essentially, if somebody comes in a courier, and instead of going to long distance, they courier it. I mean, do it faster, something like that. But
urban transportation can be way much more easier within this. You can simply try and use
because as I said, the amount of energy you would probably have to keep the sort of vacuum going, and thing would probably be much higher, right?
So in order to keep the vacuum going, there is this competition that Elon Musk announced, in which I was one of the finalists. My team was one of the finalists. And we had tried to build the mission in there, and it was for a scale of 1 kilometer. The challenge was that you have to send in a pod which can traverse through the 1 kilometer distance in there. So this was doable within the scale of 1 kilometer, where they will pump out air each and every time when a new vehicle enters. That's the way they were doing it within. This is located in California, in SpaceX headquarters. So the idea is that you could try and do this each and every time when a new vehicle enters, and that's going to be pretty challenging. And all of it is depending upon the scale at which you're doing this.
Scale and synchronization, right? Any loss of synchronization could have bad effects.
Say the tube vacuum okay. Even if you, let's say you're talking about external things, and if you maintain 50 kilometers, 100 kilometers, okay, perfect vacuum, you're able to make it. I'm just asking as a layman, as a physics person, what will you say? What are the impact of an object, material, container, some kind of freight? Then maybe inside that box is a human being. It could be a tube. It could be a medicine. It could be some kind of practical benefits of, it's remarkably exponentially greater for human beings when we achieve this successfully. But what exactly happens at something which moves at a specific speed and gears up speed much more? It may be externally, it may be vacuum, it may be there's no friction, everything is going through the tube, but what exactly the impact on the box itself, on the content?
You're talking about the box in terms of damage, physical damage, or something like that.
Yeah,
Like, I mean,
No, I mean, what I think Rajmohan means is if you are sitting in a pod,
yeah,
what will be the impact on you physically?
yeah,
Is
okay,
there, yeah, basically because you're traveling at a faster speed,
yeah.
the
So
forces of gravity or
the
things.
yeah, so we have already managed to achieve transonic speeds in terms of Concorde flights, and they were around for some time, and then they were discontinued because they were not economically viable. So in terms of physical health itself, there isn't going to be a lot of damage when you're traveling at say 330 meters per second. And the another key issue that I see here in terms of transportation is that to see how exactly, if let's say there is an accident, the worst case scenario, how exactly are you going to get out of it? That's another safety constraint that you are trying to look at.
Okay. Like you are in the underground and
And
somewhere the train
some
stops. You should be
so
have at least
you
walk
have
for
to get out of it.
100 meters
So
and get
what are
out.
your safety or accident mitigation
Okay.
parameters here? That's
So
another key challenge.
yeah. So essentially, there are two challenges: one the physics part, and the other the engineering part.
Engineering part.
Yeah.
So more than engineering, the ecology part, where we have to make this
yeah.
feasible and workable.
Yeah.
The advantages are that speed and energy consumption becomes very low. You can go at a very high speeds at a low
Lower
kind of.
energy. Yeah.
Okay. So when I think of as a person not connected with science in any form, whether it's technology or science, I cannot, whenever especially people talk about physics, I cannot stop but thinking about what Paul Fairbairn said. Well, boss, science is always there. Good Lord, look around you. How much of science has happened? Technology has improved. Earlier we used cauterization, now we have laser surgery. So many years, centuries have passed since Newton discovered those laws. And he said maybe Einstein and to some extent Heisenberg just peeped into that. And these quantum fellows are always, they are confused and he leaving everybody's confused. So when we talk about that, it's 1666, correct? When during the pneumonic plague, Newton discovered laws of motion, laws of optics, and everything. So all those laws, gravitation and all that stuff. But maybe technology was not there, engineering was not there. So detection of gravitational waves. Okay, that's what I was when I said in Twitter, everybody talked about LIGO. What is that LIGO and what is this detection of gravitational waves? I mean, what is it habit in us for us human beings? In what way it
So
can improve our lives?
you started the question really well. You started right with Newton. So that's where the entire Lego things
Yeah.
again starts from. So Newton came up with this model for gravity, as you mentioned during the plague. He comes up with the entire model as to the same thing that attracts the apple is the same thing that's going to attract moon as well, and that's gravity. So there is a particular form into which his formulated gravity, he's put it in there, is F equals g into m1 m2 by r square. The two masses are going to attract with the specific inverse square law. And then, like almost 200, 300 years later, Albert Einstein comes in. Albert Einstein talks about how gravity is going to bend space-time, how matter is going to bend space-time itself. So instead of thinking about space as an extremely flat surface, he's talking about curved space and how exactly space is going to curve along. He imagines space like how you have a trampoline wall. You have the entire trampoline wall. You don't really let's say there is a huge weight put in the middle of it, and there is a smaller ball here, and I'm going to try and pass the smaller throw the smaller ball along the lines of the trampoline. What's going to happen is this particular weight is going to impact the trampoline. It's going to create a curve in there, and that ball is going to come in, spiral around, and then try and crash into this ball. So this particular effect that gravity or larger masses have upon space-time, that's what Albert Einstein starts categorizing and eventually brings into his general theory of relativity. So that is this particular factor, 8 pi into g divided by c power 4. So this is kind of just like how you have a gravitational constant. Gravitational constant is 6.67 into 10 power minus 11 Newton meter square per kilogram square. Whereas, so you have g, you have c. C is 3 into 10 power 8. So this is the level of curving, or this is the level of curvature that gravity is going to impact, or masses is going to impact upon the space time. So that was the point to which Albert Einstein moves gravity to. Now, let's say there are at each and every point of time when mass moves through space-time, it is going to impact space-time. So basically, gravity tells space how to curve, and the space-time tells matter how to move. That's kind of the key ideas that we have in terms of gravity. Now, getting to LIGOs, linear gravitational observatories, what we try to do is try and see how exactly these gravitational waves, or the curvature within the space-time itself, is going to interact with matter, and how we can try and observe that. So when two objects collide, when two bodies collide, that is going to in turn let's say affect space-time in a certain manner. That is going to propagate, or the gravitational wave itself, that is going to propagate through a larger distance, and that particular propagation created by the two masses colliding, that's something that we call a gravitational wave. And a gravitational wave, when it comes in, it's going to be incredibly hard to detect because it's at such extremely smaller scales. So what people in LIGO did, or gravitational observatories do, is they create two perpendicular lasers. One lace. So essentially, you have a single source that is a beam splitter. You use the source, split the two beams. You get the waves are going to propagate in a perpendicular direction. One is going to be this way, the other is going to be along this direction. And the moment the gravitational waves start coming in, it is going to it is going to impact or try and slightly shear one of the two laser waves away. And when these two waves get back to the beam splitter, there is going to be a slight wave phase difference. And that is exactly what the observatories are trying to map into in terms of LIGO. And the first such detection from a cosmic event where two huge black holes collided, I think they've given it a number. I'm not exactly sure of the number. And that event was recorded sometime in 2015. And that's what you saw quite a lot of times on social media. And as technology starts improving, as technology starts getting better, we'll see more such events. We saw a collision of neutron stars like 2017, 2018, sometime then.
Yeah.
So,
okay. So essentially, a collision of black holes in a universe far away, which is probably 1,000 years to whatever it is, light years away, will have an impact now on our observatory. That's what we are saying. So, so this is, so you really require large masses to collide for this to happen, right?
For us to be able to detect this easily.
Exactly. So
even two masses are right now, let's say you take up two balls and put it together, there is still going to be a gravitational wave, but that's not detectable.
Not detectable, because the curvature that we get on normal objects could be very less, correct?
Extremely low. So the factor, that's why I gave you, it's 8 pi into g divided by c power 4.
So
that's, so this is 10 power minus 11, it is c power 4. So c power 4 is 10 power minus 32. 32 plus 11 gives you 43. 10 power minus 43 is the kind of impact that normal
day-to-day. So that's why we don't get affected by the curvature is not there. Only large bodies can show some curvature, right?
Suresh, just before you ask, okay, I may have understood wrongly, but all these things, can also enable us to bend the space-time. Like, for example, there is two objects collide. What happens? You detect, you are saying. If we are able to detect that, what exactly happens? So using that, we can also the graph of time.
Graph of time, like when
let's say I personally feel what Rajmohan is asking is, can you do something which which are sure you can the curvature of the space time, can you manipulate? I personally think that those amount of you won't have the energy to get anywhere close to that.
That's true. So we can't really we still haven't gotten to that point yet. It might happen like years later, but we aren't really there yet.
Yeah. So tell me another thing, Nanda, just as a follow-up to this, is that how long can you detect this? I mean, you detect it first. How do you know at this point, or you're just observing all the while, and at one point it happens because you have not observed the collision of that, right?
Yeah.
because collision has already happened sometime, but
Time.
the time that the waves propagate, and I think
Yeah.
the time that the light propagates must be the same.
Yes.
So anyway, you don't measure light from there, right? Mostly you are
Yeah.
using your
Yeah.
telescope, so you are measuring only the waves.
Waves.
So when the gravitational waves probably have the same speed as any electromagnetic wave, and therefore you are so essentially they just keep the LIGO pointed out to space and just keep observing, and one day
It's
they
LIGO is not. It's not like pointed in the sense that you have
correct
a
correct
telescope pointed there. It's
correct
just
correct
two lasers on 4
lasers which
kilometers
are continuously going on,
going on. Yeah.
and you are measuring how they recombine that. So your partially silvered mirror type of
Mirror.
thing to
Yeah.
diverge them, and then you converge them again,
Is it
Convert
right?
something
them.
like series
So
of
if you
photons? Series of photons emitted?
uh,
Yeah, you could say that lasers are extremely coherent, so you could call
Okay.
them a series of photons.
yeah, so essentially what is going to happen is when they meet back, if the distances are correct, you will see a single source of light. If
Yeah,
not, you will see some pattern like what you see in
like
atomic
yeah,
spectroscopy.
exactly. It's a kind of an interferometer, as you were talking.
Okay, okay. So they don't know when it is going to happen, but one day if it happens, then you understand.
Yeah. So the
Okay,
another key challenge is noise, as usual.
yeah,
At this
yeah,
level, even ordinary, earthquakes, earth
uh,
moving assets,
could
that's
could
going to create
a
a change
noise
here.
and yeah,
So for us
and
to be able to detect this, we'll have to eliminate all kinds of noises
yeah, and
and
secondly,
be able to.
also it is like you have to correlate with astronomy to know if that event has happened, right?
Yes, definitely. I mean,
Uh,
for
uh, uh,
fundamental physics and experimental physicists and astronomers keep collaborating a lot of time, and that
yeah,
helps.
yeah, because otherwise you don't know. Real,
No
like you said, is it from a real event or is it
event
a
or not.
noise? Yeah,
Yeah.
okay, great, great. Yeah, a lot more questions, but I think I'll just check with Rajmohan. What's the time, Rajmohan? We still have some time
Yeah,
for
some
2 3
little bit.
questions.
Yeah, we can go little bit.
Yeah, sure, sure. The other one, like Rajmohan said, one of them, of course, was LIGO and electron. Sorry, this waves here. But my other thing was the discovery of what the Higgs boson, right? The
Yes.
very
The
enticingly
God
named
particle.
God's particle, so that everybody. And this, of course, was like a front page news on even a normal newspaper type of thing. So, what is this boson? And from whatever I understood, it is not like it's detected in sense of detected, but rather it is an percentage guarantee that it has been detected. Like
Yeah. So yeah,
it's
Six Sigma. Six
the
Sigma.
Six Sigma or Seven Sigma type of
Sigma.
a thing. So what is this actually?
So they in physics there is this particular joke that all of physics is either particle or fields.
Yeah,
They'll keep saying at one point of time they said all matter is made up of atoms and atoms are indivisible.
correct.
And we started modifying those theories. We started saying that there were protons, neutrons, electrons. So after that, we could go subatomic, and we were able to, even more see what exactly protons and neutrons themselves are made of, and that's how you get to what we currently call the standard model of particle physics or standard model of physics. Basically, these are the very things that make up the universe, basically.
Universe. Yeah.
So there are two kinds of particles in there. One, the fermions, two, the bosons. Fermions obey Pauli's exclusion principle, and bosons don't. So for popular fermions include electrons. So fermions in turn are further subclassified into leptons and quarks. And quarks are what make up protons and neutrons. And electron is a lepton. So within the field of bosons, you have photons. The fundamental force of the fundamental work of the photons or the bosons is that they're supposed to be carrying particles. So when two other normal particles or two other fermions interact, when there is a particular way of light or when there is a particular force being exchanged between the two, these bosons act as fundamental force carrying particles. And so once we start bringing in the entire idea of gravity and how exactly all the passes begin to get mass, it is this particular Higgs field. So Peter Higgs hypothesized this in, I think, in the 70s. He fundamentally postulated the existence of this particular particle called the Higgs boson that is going to interact with each and every one of the other particles, and in turn it's going to impart them their mass, and that in turn makes that particle have let the particle has its mass. And that's exactly why it started being dubbed as the God particle, and why there was so much hype around it. And CERN started working on this. They built very many accelerators to get there, and then finally LHC did the job. So even within the LHC, it was very specifically two experiments: Atlas and CMS. CMS is compact muon solenoid. The idea of a particle accelerator is to essentially sling two particles at extreme velocities, so that the two particles are going to simply splash apart, and you can start observing what exactly is present in there. And at a certain point of time, you start calculating those energy signatures, see what exactly those particular particles are made up of, and you would be able to arrive at whether you have found whether if there is any evidence to what Peter Higgs postulated initially. And that is where the entire sigma or the variation calculations start coming in. Again, as with LIGO, there is going to be a lot of noise in this case. We'll have to narrow down upon and say this particular energy signature is what corresponds to the Higgs boson. And that's why they say there is a particular guarantee. You have 6 sigma guarantee or 5 sigma guarantee, within which you are able to say with a certain confidence that you have detected the particle actually. And they were able to say that only in 2012, 13, I think, sometime around there.
Correct.
No, I mean, like, okay. So it is not yet 100% sure that we have found boson, Higgs boson. We are not yet found.
We are able to say with a level of confidence that we have found it. So we can definitely claim that we have found the boson.
So then we can say the whole light is itself is a play of boson.
Yeah, of course. I mean, light is made of photons, and like photons are light particles.
Okay, so you mean okay? You talked about large colliders and all that, but you also just mentioned. I mean, I'm asking as a curiosity: is there any resistance from the governments to carry on this kind of experiments? The amount of money is a huge amount of money that you need for these kind of things.
Definitely. Experimental physics at this level is going to be like extremely costly, and you're going to pour in millions and billions of dollars to try and get there. So people have been talking about the future circular collider. So this will be the next iteration of LHC to see what exactly or how exactly we're going to go about there. So there are even arguments even amongst physicists as to whether we should try and build this. So the purpose of the LHC was to try and discover the Higgs boson. We have done that. We can confidently say we have gotten there. So what exactly are we going to do next? That was the question that's being put forth. People are talking about how exactly string theory is going to try and change the fundamentals of physics, and whether we have. So in order to ensure that whether string theory can be proved, whether if particles itself. So right now we are at a stage of particles. How exactly are these particles built? Can there be strings? And so in order to investigate into more of those kind of questions, we are trying to say the FCC needs to be built, or the future circular collider needs to be built. So that's what one group of physicists are saying. We have enough evidence to say that string theory is a viable form of theory. We could start doing experiments, large scale experiments upon this string theory. There is another group that says no, you're rushing. You're essentially rushing into the entire thing. This amount of money is rather well spent on some other form of experimental work and some other experimental research, like dark matter that we discussed earlier. Is there a way we could define or design better experiments to detect dark matter, which was supposedly undetected earlier? And that's really catching up. So it's also about a kind of theorists right now are at a stage where still debating as to whether they should try and build these kind of large colliders, FCCs, or future circular colliders.
No, I just before I ask you the final question, I have one more supplement to this since you mentioned string theory. Again, I keep reading a lot, but at a very high level. As you said, there seem to be two groups. One which says string is everything. I think Susskind and others are part of that, where they do that. I mean, they are into string. But of course, string looks like it works only in 23 dimensions, something like that. And look at the mathematics. Penrose in another place, I read him. Penrose says that, string theory is wonderful, beautiful to look at. It's like you're going into a city with multiple roads and you get lost in one of the roads because it's beautiful, but you never reach a destination because string theory has not yet given anything which can be disproved. I mean, it's not made a prediction or something like that. There seem to be two opposing camps which are going on, one saying yes.
So because that kind of ties into this debate as such.
Okay.
So there is particular this particular group of physicists say you're being misled by beauty. beauty is not what you should be looking at. So just because it's beautiful, it is not particularly viable to try and pour this amount of money into this. We need more evidence, something more concrete than this. You guys are simply being taken in by beauty and symmetry and all, just because all our earlier theories were symmetrical and perfectly beautiful, and we had supersymmetry last time, doesn't mean that we will have it again. And that's what the camp that opposes FCC says. And the camp that supports FCC says, no, this has to be the way. We'll have to come up with better evidence. We have enough evidence to support our hypothesis, so let's go ahead and build it. So string theory is still kind of the child where the parents fight for custody or something like that. So.
No, I'm saying it's more like they say this is a child, and the other guy is saying it's not a child.
Yeah, that could be so.
Because if they're fighting for custody, they would want to build it anyway. But it's more like no, this is not a good.
This is not proven yet, or something like that kind of debate keeps happening.
I care about it is it is unfalsifiable theory is what I keep hearing this word. That is, it doesn't predict anything that you can falsify.
So that's exactly what it is. So the predictions are like, we don't know whether these predictions are verifiable, and we don't really know how exactly we're going to go ahead and
verify them. Okay. So before I'll just ask you the last question before we conclude. Is one thing. So now this is something which we ask in all our questions, is that I know that when LIGO came out, there were certain people in India were also labs were involved, and Indians were involved in this case. So you have also been in India. Of course, you have been in engineering here, but of course, I'm sure you would have started interacting something. But how is it? Do you think things are happening in India? Which institute are doing physics, and what seems to be the focus in the Indian academic institutions as far as physics is concerned?
I think it's like really catching up in terms of whatever we're doing in terms of modern day technologies. And India has been an associate member of CERN, I think, since the 2005-2006 times, and India has been a party to the ITER project that I just described earlier. And we have Indian teams collaborating. Science is always international, and we need expertise from all countries. And I think close to 45 countries have collaborated on CERN so far and building the LHC so far. And Indian groups very specifically have contributed to a whole lot of it. I'm way much more interested in the quantum technology part of it, because that has an immense amount of implications. IISc Bangalore has a very specific master's program catering very specifically towards quantum technology, which I believe they started last year in terms of quantum computing. And then there is a particular group in TAF for Mumbai, Tata Institute of Fundamental Research, they work on quantum control and how exactly we're going to control the chips, qubits chips that I was talking about earlier. They work on TAF. And then there are a few in Harishchandra Institute, Delhi, few groups working very specifically on quantum computing. And I think it's really looking to look up. I think most countries have kind of set up initiatives or programs, and India has done that, I think, last year or something. So
very good. Next to that, I just one quick question as a supplement to this before I wrap it up. Looks like physics from being an individual pursuit nowadays seems to be that it's now going to be a very collaborative effort. There are going to be very few scientists who are thinking of things on their own, because at least in the experimental field looks like that. What's been your own experience?
Yeah, personally, I will agree with that. So if you're going to do large scale experiments, the kind of huge experiments in terms of CERN and LHC, building particle accelerators, building fusion reactors, you need expertise from a wide range of fields. I've seen that myself many times. I very specifically specialize in electromagnetics, and I've been able to contribute to controlling magnetic fields and working on magnetic fields alone. But magnetic fields alone do not form the...
Correct.
I think there is some connectivity issue with him.
Yeah. Just let's wait for him to come back for a minute.
You still there?
Yeah. You're back now. You're back now.
Okay. Sorry about that.
Yeah. You were saying that you were an expert in the magnetic field, and
so I specialize in this particular field and I've been contributing to this particular area alone. But you need electronics, you need mechanical engineers, you need fluid dynamists, you need theoretical physicists who work very specifically on these areas to essentially give us how exactly we're going to go about testing these theories. That's the main job of a theoretical
Oh,
physicist.
okay, okay.
And then you have the kind of expertise that is required is vast, and
Mm.
when we kind of start bringing in these people together, we have the kind of large scale experiments that you see.
Okay, okay. Right. So
Suresh,
let
just out of,
yeah,
before you wrap
yeah,
it up.
I will just wrap it up.
No, one
Uh,
second. Before that, I just want to ask out of curiosity,
uh,
where are we on the Stephen Hawking? Maybe when he came some 20 years ago, 30 years ago, a brief history of time.
Yeah,
So maybe around that time, 30 years ago, where
89, I believe, 1989.
89,
yeah,
yeah.
around 80s, yeah, in the
Yeah.
80s.
So where are we? I mean, like, he says that there is a, you wonder, is there must be some intelligence somewhere in the world out there, some kind of alien stuff. That's what we could relate it as. Maybe some kind of different form of intelligence. Where are we? Is there any kind of
I mean, as far as I know, there hasn't been any evidence found in terms of alien contact or anything. Carl Sagan came up with this
yeah,
entire idea of sending the Voyager up there with saying we Earth is here, we are humans, we are here in every possible language. That was way back when the Voyager was sent up, and that's how you got the pale blue dot image that is extremely famous right now.
Yeah.
So that is this particular equation called the Drake equation that actually tries to calculate the probability of humans establishing alien contact. But uh, as far as I know, there is absolutely no evidence of. It looks like we are all alone in the universe. That's what it looks like right now.
yeah, okay.
Maybe.
So essentially, to just rephrase what Nanda is saying, alien contact is very much possible in movies, but real life is a problem.
Yeah, yeah. I mean, Steven Spielberg could come up with something like that, but yeah.
No, in fact, a few days back, I was watching this movie called Signs, which again was about aliens, a bit of aliens and all that. Yeah, so let me summarize what is what we discussed today. At first, let me thank Nanda for joining us, and it's been an extremely enlightening discussion because we learned a lot, and I'm sure whoever is watching it now will also learn a lot about what's happening in the world of physics. Um, Now, it is said, like first, the important thing that Nanda mentioned, where we spoke towards the end, was that physics has become a huge collaborative effort rather from the time of Newton sitting under a tree and falling. In fact, early in the 20th century itself, it has become more and more specialized. Like Landau, the great Russian physicist, was seen as one of the last generalists in the sense that Landau was the one who know almost everything in physics type of a thing. And there is later day Susskind, who is a physicist who teaches physics in I think Stanford. He wrote a book which was titled Theoretical Minimum, and he said why he chose that thing was that if you wanted to go into Landau's course, you had to pass this theoretical minimum. You had to know. And Susskind says that the theoretical minimum that Landau said you have to pass was all that Landau knew. And he said nobody in that time knew what Landau knew. That sort of generalists, I don't think are any longer there. We have got to the era of specializations, and as Nanda very clearly said, to build one reactor or something like that, you need specialization from so many areas, and each of them has to work with the other to understand what it is. And if you had watched our earlier neurogenetics program, that's where Dr. Surabhi Viraguna also said the same thing, that it is no longer like genetics is separate, neurology is separate, and the patients are separate. You have to gel all of them together, and then genetics is using computing, they're using big data, and everything collapses. So the world is going towards a larger and larger collaboration part, right? You're going to find lesser and lesser Einsteins and Newtons, and more of a discovery happens, and it is attributed to some 10 teams all across the globe. Now, we spoke about many of the modern sort of innovations and modern problems of physics, starting with what is dark matter and dark energy type of thing. And then we proceeded to see what is quantum computing and how it will change computing going forward. They're still in experimental stages, but yeah, things are improving, and we don't know. And the sort of money that's poured in, I'm sure, it all depends whether it's 5 years ahead or 20 years ahead. We don't know, but it will happen. And if that happens, then there are going to be impact on the security part of it and how we do security. And as Nanda said, you're talking about sort of a superimposed state, and we're talking about tangled entanglement, and so you'll find that computing people have to understand quantum mechanics. It's just not going to be easy, but yeah, you'll have to understand those states. And then we spoke about the other aspects of science that we're looking at the how do quantum theories impact our measurements, and how those can lead to better uh, detection in medical devices, better detection in GPS systems, and so on. And then we have spoken about things like how do you detect gravitational waves, how they detected the God particle. And we also spoke about something like how a hyperloop would revolutionize free transport, what are the challenges and all that. So as you see, most of what is spoken by Nanda are problems that are getting addressed, solved in experimental fashion, which will have potential uses. So we really are on the edge of technology that we spoke about today. And for this, I have to thank Nanda. It is an extremely lucid explanation from him for us to understand. I mean, all laypersons like us could understand. So once again, let me thank him for taking his time to talk to us. It has really been wonderful talking to Nanda. Thank you, Nanda, for
Thanks very much
being
for
here,
having me.
and we
Yeah,
are really pleased to have you here, and it's a privilege having you here.
it was
Uh,
really wonderful. Yeah, it was really wonderful. Thank you, Nanda. Thanks for
Thank
being
you.
part of
Thanks
it.
for having me.
Thank you.
Thank
Yeah.
you.
Bye.